Okay, good morning, everyone. Is it audible? And yeah, I would like to start by thanking the organizers for putting together this wonderful conference and for the Hamburg group for being such a fantastic host, and of course, by giving me the chance to speak here. So the title of my talk has two parts. The first part is moonshine. Okay, so what is moonshine? Well, we all know vaguely that it's a connection between finite group representations on the one hand and modular objects on the other hand. So in the 90s and the 80s, we have seen a lot of activities surrounding the monstrous moonshine. And since 2010, we have seen a lot of a new wave of activities regarding so-called mature moonshine and umbro moonshine. And the reason why many of us care about it is its relation to the K3 symmetries and especially string theories compatified on K3 surfaces. So I have given a review talk on that part of the development 1 month ago in the strings conference. So today I'm actually going to do something a little bit different. Namely, I'm going to talk about some results on this different type of mathematics that we have not heard a lot about so far in this conference, namely the classification of certain type of Jacobi forms. And although this result can just be seen as isolated result on analytic number theory, but it is very much motivated by the question about moonshine, namely, where does moonshine appear? In particular, what type of modular objects are relevant in terms of connection with finite groups. And another motivation is about some certain Mach objects called Ramanujan's theta functions. So not only have they spurred this whole development of the theory on Mach modular forms, but also it has a lot of connections to other fields in mathematics, for instance, the combinatorics, and many of them are known to be connected to certain quantum invariants on 3 manifolds. But why are they so special? So among all the possible Mach forms, why are these Ramanujan's theta function better than the other? And the third question comes from the fact that many of you have heard about Mach modular forms because they naturally show up in physics, in the counting of black holes and other BPS invariants and so on. But for physics purposes, we want them to have integer coefficients. So what are the generic coefficients of a Mach modular form? When do they have integer coefficients? Okay. So the results in terms of the classification, first, I think sufficiently answered these questions. And it has some very nice features. For instance, you can sort of rediscover Niemeyer lattices if you want from Mach Jacobi forms, surprisingly. But it also points to some surprises. So the answer, in one sentence, will be a classification in terms of the geometric condition, namely the genus 0 groups acting on the upper half plane. And it will tell us the condition for the coefficients to be integers, and it will lead to some surprises in Moonshine. So we thought we could answer this question and hence have a better understanding of Moonshine, and hence we'll be able to sleep better. But in the end, this new result actually tells us that there's more questions to be answered and more surprises in the connection between modular objects and Mach modular forms. So the plan is I'll start with some background, not just to introduce the context, but also to introduce the relevant objects that we'll be talking about. Then I'll briefly tell you what the classification is. And finally, we will see what it says about Moonshine. Okay. So the first part of background, let's briefly review the story of monstrous moonshine. So then we start with a J function, which is a function on the upper half plane with the property that it is invariant under SO2Z generated by these two moves. So instead of thinking about it as a function on the upper half plane, we can think about it as a function just defined on the modular curve, namely this keyhole fundamental region. It has another property, namely if we take tau to be I infinity and we want to know how it behaves like this, where Q equals e to the 2 pi I tau. Okay, so it has a pole at I infinity and followed by a 0 and higher order terms. And the nice thing is that it is actually a unique function such that this is satisfied. So we can think about it as mapping from the compactified version of the modular of this curve and then to CP1, adding the point of infinity, and this is actually an isomorphism. It's, in other words, this fundamental region is genus 0. And because it's an isomorphism, so we fix this and we fix the subleading term, and that fixes the isomorphism completely. So this is unique. And another nice thing about it is that if we start looking at these higher order terms, then the next leading coefficient is 196884, which we split into two parts in this way. And this is the third coefficient. We split it into three parts in this way. And why the splitting is nice? Because these three numbers are precisely the dimension of the first three ordered by size irreducible representations of the monster group, which is the largest sporadic finite simple group. So it looks like, right, each term in the Q series is given by a representation of the monster group such that the dimension just gives, the graded dimension equals this unique J function. So that's kind of surprising why this canonical J function, canonically defined modular function, have anything to do with the monster group. But it gets only better. Namely, to establish a connection, we can't just look at the dimensions, we also should look at the group characters. So that has led to the monstrous Moonshine conjecture, and which is now a theorem thanks to the work by Franco Lepowski and Merman in '84 and Borcherds in '92. So now I'm going to write down this conjecture, or by now theorem. And it is again given in terms of genus 0 subgroups acting on the upper half plane. So monstrous Moonshine conjecture. So it says that there is a module for the monster group. We call it the V natural, and it has a natural grading, Z grading. And we also know that V natural has a structure of a vertex operator algebra, so the Z grading corresponds to the L naught eigenvalue if you want, such that its graded character, namely, we now want to look at the group characters and not just the dimension. And is the unique function such that it acts it induces the isomorphism from the fundamental domain of some subgroup of SO2R, as I said, to the sphere. And of course, if you look at that, it has the Q expansion like this, and it uniquely fixes this function. And the key here is that these groups, by definition, are again some genus 0 group. And this is true for all elements of monster group. And there are about 10 to the 55 elements, but thank God there's only a few hundreds of conjugates classes that we have to check. So the question, what are these groups? Well, for that we have to introduce the so-called Akin-Lehner involution, which will be very important for us later. So for the rest of the talk, M is a positive integer. And then we define the congruent subgroup of SO2Z to be given by SO2Z elements such that this lower half corner element is a multiple of M. Okay. And in the Moonshine context, this M will be given by the order of the element P, order of the element G, as we can see from, for instance, the VOA or the CFT argument. Okay, now we define for such an M the group of exact divisors So what are exact divisors? They're divisors such that it's co-prime to its remaining factor in the thing. For instance, 4 is an exact divisor of 12, but 2 is not. Okay, and why is it the group? The group structure is given by the multiplication such that, I'll write it here. The multiplication is modified by the dividing the GCD of the two numbers. So for instance, every group, every exact divisor, every number multiplied by itself gives 1. That's why it's called involution. So for a given K, which is a subgroup of exact divisors, we can define such a group in SO2R. I'm not going to give you the exact definition, okay? But for each exact divisor, we attach some elements, some actual elements to the group. So for instance, if M itself is in the group, then there's some certain element of this group that will map tau to -1/m tau. So it's a variation of the usual S transformation. So the second, that finishes the first part of the background. And I told you what the genus 0 group in monstrous moonshine more or less look like. Before I go to the second part of the story, background story, is there any question? So the second part of the background is, what are these Mach forms that we are going to classify? Well, let's go back to Ramanujan. For instance, in a letter to Hardy, he wrote down some functions that looks like this, with a very simple expression +1, okay. And then if you expand it, it has simple coefficients like this, 1, 1, 1, 2. So the coefficients grows very, very slowly, okay? And these functions have many nice things about it. Well, for instance, it's known due to Lorentz-Aguirre that it's related to the to the quantum invariant of the Poincare homology sphere, the three-manifold sigma 2, 3, 5, for instance. But, and he also defined, Ramanujan also wrote down a similar function, chi2, but we're not going to talk about it. But what is its modular property, okay? And this was answered by Zweichers in 2000, in 2005. They say like, okay, if you add first a prefactor Okay, we shift the powers of Q a little bit, and we add some correction to it. And we do the similar thing for chi2. Then they actually transform under SO2Z, although the function itself has no nice property under SO2Z. So this property is called the Mach modularity property. And what is this G1 and G2 are some modular forms. I'm not going to specify. And this star operation is given by up to not very interesting prefactors, a non-holomorphic integral of the modular form. Okay, so despite the fact that these are holomorphic, this will no longer be holomorphic. However, the completion, well, the corrected thing transform under SO2Z as opposed to the original holomorphic thing. And an even better way to think about these chi's, this Ramanujan's function, is that instead of seeing it as a vector, okay, that transforms in a certain way with a certain matrix of multipliers, we can think about it just as one single function, but now with two variables. Okay, so how do we achieve that? Well, before saying this, before telling you this, so forget about the Machness for a second. Just, we have seen this kind of situation before. Sometimes a vector of modular forms can be combined into one function with two variables that transform nicely, and this is called the Jacobi forms. Well, we have encountered that often in physics and in math. For instance, if you have a two-dimensional CFT with some U1 grading, for instance, coming from the supercurrent, then the partition function will be a Jacobi form. And relatedly, you can write down an elliptic genus of any Calabi-Yau manifold. It will also be this Jacobi form, this two-variable thing. So we are going to do the same thing for Mach. So for any positive integer m, we introduce first the index m theta function. We denote theta m, which is a vector and with two m components. And this function has two variables. So if you want, it's really just a theta function, nothing interesting, like this. And you sum over all the integers, that equals R mod 2m. So it's a certain lattice, and the discriminant lattice that's labeled by R. And also the index m elliptic action. Namely, if you have a function tau z, and then you act on it by, let's say, m/m with certain two integers, and then it's mapped to, okay, you just shift z by an integral amount given by these two integers times some m-dependent factor. And the modular action of weight k, similarly, what you do is you map tau to the usual gamma of tau, which is a tau plus b and c tau plus d, and then shift z, rescale z in a certain way like this, and plus some, again, some n-dependent factor, and the weight, usual weight factor here. Okay. So once you define this, we can discuss the property of this Ramanujan theta function. Namely, if you define a two-variable function, and by combining, Q, this corrected components, and with theta 31 and 11 and 19 and 29, and again similarly for the second component with some other theta function of index 30, and anti-symmetrize when you shift a z, then this function, two-variable function, is invariant under the action of index 30, weight 1 action for all SO2z, and under the index m elliptic action for all z cross z. Okay? So this is very remarkable. And this is due to, again, Zweiger's and later refined in the work by De Boker, Morty, and Zagir in the year 2013, I believe, 12. So this is, then we define another two-variable function, now holomorphic, by simply erasing the correction term. Then we say this phi is a mock Jacobi form of weight 1 and index 30. So the 1 and 30 clearly comes from its transformation property here. Okay? And then to recap, a mock Jacobi form is a function such that if you add in the correction term in a very controlled way, it transforms exactly like a Jacobi form. So that finishes the second part of the background. Yeah, the harmonic mass form. Yeah. Yeah, but yes, but I mean, basically it's the same thing by treating this as vector value. Yeah, huh? Yeah, so it's repackaging of that. Yeah. Any more question? So the third part and the last part of the background is what's called the Umbro Moonshine. And this was developed by John Duncan, Jeff Harvey, and myself in 2013. So I spent too much time with mock Jacobi forms in the last 6 years because of this. So the construction is the starting point, by taking Niemeyer lattice as the starting point. So a quick reminder on what a Niemeyer lattice is. We know due to the theorem of Niemeyer that there are, in 24 dimensions, exactly 24 inequivalent even and self-dual lattice. Okay, we all know, we all love even self-dual lattices with positive definite signature. And there's one of them that's distinguished, that's the Leech lattice, because it does not have root vectors. The root vectors are the shortest vector allowed by the evenness condition. And there are 23 others, and they have full rank root lattices, so root systems. So they are unions of ADE root systems that are exactly those with cosinear. So 23, we saw K, X, which are root systems that are unions of ADE with a unique cosinear number M. What do I mean by that? Well, for each component, it has a cosinear number, and the cosinear number for these 23 has to be the same. And you can spend 5 minutes to convince yourself that there are exactly 23 of them subject to these two conditions. And these are exactly the root lattices of the remaining 23 Niemeyer lattices labeled by the root system. So the construction of Moonshine is to take this lattice, and on the one hand, you can define a finite group by taking the automorphism group of the lattice. Well, strictly speaking, you take the interesting part, namely you mod out by the wild group of X. And on the other hand, you can write down a mock Jacobi form of weight m, of weight 1 and index m. Okay, I'll introduce this symbol properly later, but it's a mock Jacobi form. And such that these two are connected by Moonshine in the following sense. So first, you can generalize the construction of this and attach a mock Jacobi form of a higher level. So again, this will be given by the order of G, just like what we have seen in the monstrous case. Okay. And for every element of the finite group, you define there using the automorphism of the lattice. And because, as we have seen in the monstrous case, in order to establish the existence of representation, you need also the group characters, not just the dimensions. So with that in place, we can phrase the conjecture, namely, there X, it's very similar to the monstrous case. So let me be brief. There is a module for or a representation of your finite group and for each component R, and that's of course given by the index, which corresponds to is given by the cosinear number of the group. So such that, okay, the graded character corrected by a sort of a wrinkle and the rest is exactly the same as we have seen before, is what I called H sub G of R. And the modularity of this guy is that this is exactly, you know, the component of the mock modular form. Okay. So in some sense, it's completely parallel to the monstrous Moonshine case. except for this wrinkle and the crucial fact that these are Mach now. So this conjecture has the existence of such a representation has been proven by Terry Gannon and Griffin, Duncan, and Ono. But the most interesting question is, of course, to construct them. And there's a few constructions around for 9 of them. And again, if you are interested, you can look at my review talk in Shrinks on this. But I just want to stress that, so due to Duncan Harvey and Duncan Odeski and some others by myself and so on and so forth. But what matters to me is that these are not uniform constructions, and they look like they are not the final answer. And so that's part of the question, as far as I'm concerned, is still open. And another interesting thing about Umbro Moonshine is that it's now known, due to work by many others, including myself and some of you in the audience, that it's very closely connected to the stringy K3 symmetries. But that's not what I'm going to talk about now. And so now the interesting question for me is that, you know, what are so special about these Mach Jacobi forms? If I didn't know about the Nima lattice, or even if I knew, I mean, we found these forms by doing a lot of experiment. Is there any kind of, theoretic reasons why they're very special? And so first, so it's also a very interesting question to ask, the same question to ask about these other guys for a different group, different than SO2Z, but let's focus on SO2Z for now. Well, the first thing you notice is that since it encodes the dimension of some representations, it has to be integers. The coefficients have to be integers. And even better, up to this, fudge thing, this little wrinkle, everything is positive. Okay. And the second thing, which is not so obvious because I didn't write down the coefficients, but which is true, just like in the Ramanujan's case that we have seen, is that the coefficients all grow extremely slowly. Okay, and in the world of modular form, we know that the growth of coefficients is connected to how deep the poles are when you go to I infinity. Okay, so that's, for instance, known in terms of Cardy formula and so on. But the same is actually true, you can show, for the Mach forms. So that led us to a few definitions to define the things we want to classify. Okay. So the classification result 1, which will focus on the weight 1 Mach Jacobi forms that are relevant for the Ramanujan's guys and Umbro Moonshine. So we want Z coefficient, slow growth, shallow pole, which is the same as having a shallow pose at I infinity. Then we define, okay, something like this. And this, following the work by the Volker, Murthy, and Harvey, we'll call that optimal. Okay, so how is it defined? For comparison, I also write down the definition of Jacobi forms at the same index and same weight. First difference is the symmetry property. Okay, so this says that it has to be invariant. The phi, which is an element of this, has to be invariant under the modular and elliptic action. And when you put a bar here, go to the Mach world, this is much more lenient. You just have to find some correction, G star, such that the combined thing is invariant, okay? And this is clearly a special case of this, because you can just put the correction to 0. And if you write this phi, again, in terms of the components of this guy, which depends only your original guy, which depends only on one variable and the theta function, and the growth says that here in the Jacobi form worlds, well, hence no optimal allowed. Okay, this doesn't refer to the transformation. They are really two independent properties. You can combine them into all kinds of different definitions. Then they all have to be finite at a long distance from, and we see that, for instance, this is not obeyed by the Ramanujan's theta functions. So here we want to be a little bit more lenient, but not too much. Okay, as we see, this is the smallest pole, if any, that's allowed by transformation property. So this is what we allow, and that's why it's called optimal. And before we classify, okay, let's see, because there's a very important theorem by Skorupa in the 80s, which says that at wave 1, it's very severe and restricted because this space is empty. There's no forms that transform nice and which grow, which is completely bounded. And actually, you can generalize this fairly easily and say, even if you allow the correction term, but the growth condition is so strong that it just gets killed. And you can wonder, okay, this is clearly a subset of this. And you can also find another generalization in this other direction. How about this? We don't allow correction, but we allow some poles. It's also empty. So this is the, this is the thing that when you have, this is the thing that it's the minimal thing you can do to be able to get some non-zero answer. And in the work by Zagir et al., they already noticed that this space is very restricted. And actually, we will also define a space that's a bit even more restricted. And I'll show you why it's interesting in a bit. Namely, we put a theta behind it. So it means the definition is that we further restrict that the correction term, or the shadow, this function g, has to be theta functions. You can define theta functions in various different ways, but they all turn out to be equivalent. So whatever definition you have in mind is likely to be the correct one for theta functions. So the classification, the result, the first has two parts. The first part says that, well, if you restrict yourself to the world of Mach forms, at the weight 1 and then so this is work with John Duncan. The weight 1 Mach Jacobi forms has bad news for physicists, transcendental coefficient unless the shadow is given by theta functions. Okay. In which case, you can rescale it such that it has integer coefficients. So this is the motivation to classify this. And to state the classification, we want to split it into eigenspaces. Under what? Under what we have talked about, the Aking linear involutions. So we split it into all possible eigenvalues, sets of eigenvalues under this involution, for one for each exact divisor of M. Okay, so what does that mean? Because it's all involution, so in particular, it's all, the eigenvalue is all 1 or minus 1. So how does it act on it? It acts, well, let me not give the details, but basically it acts by theta A of n times r. So it's shifting the components around in a given way. And this an is determined uniquely in terms of the divisor m. Okay. So, well, the remark is that if alpha, your given alpha maps m to plus 1, then this space has to be empty, okay? Just because at weight 1, it has to be symmetric, anti-symmetric under z goes to minus z, and that's exactly what this guy is doing. So the result is that has dimension 0, 1, if indeed m gives minus 1, and if the genus of this guy is 0, and 0 otherwise. That's all nice, but it's even nicer because this gives a finite list. This gives a finite list. Actually, you can show that the dimension of any way 1 Jacobi form that has slow growth, that have non-transcendental coefficients, is just 24. Okay. Before DMZ has done the experiment, goes up to AM equals like 100 or so, but We have done it for infinitely many, if you want. And there are 39, I won't give you a definition, 39 symmetric ones, which are unique up to rescaling, of course. So this overspan this space, but they are natural in terms of symmetries under Acting-Leonard. From these 39, 23 of them have moreover, they all have integer coefficients, of course, that's have positive integer coefficient. And those are exactly the Niemeyer lattices. So in some sense, mock Jacobi forms, if you don't know about Niemeyer lattices, this is again a way you can discover it. And all Ramanujans, Mach theta, are in one of these forms. We call them one of these 39 forms. Again, you have to shift the powers by q sometimes, but that's it. And also, we know that, have seen in the context of monster, that we have a help module, so this unique modular function for each such genus 0 groups. And this actually plays a very important role here. It determines, you can reconstruct the Mach form from the help module in a rather tricky way, but nevertheless, there is a way. And last remark is that it seems that many of them have these particularly symmetric Jacobi forms have a role in the quantum invariance of cipher 3 manifolds. So this is something we're trying to understand better now. So I won't write down the theorem. Let me just say it in words. That you notice that we have excluded the cases where, you know, M, this index, is a part of the subgroup of your exact divisor. Because whatever number you have, M, it's always the exact divisor of itself. So how about them? What's their role? Well, we thought we will complete our job. So this is a theorem by, again, with John Duncan, which we hope we'll put out sometime before the end of the year, which says that they play a role in way 2. You can try to do the same classification in way 2, which is a different world, and where you have many optimal Jacobi forms. And the result you have is actually that way 2 is 1 if now you have, it has, okay? And it's larger than 1 otherwise. So it's actually reversed. Only genus 0 guarantees not the existence, but the uniqueness, okay? So for instance, and then I will switch to the third part of the talk very briefly, namely the Moonshine part. What does this exercise tell us about Moonshine? So an urban legend is that Moonshine is called Moonshine because it's so much bullshit. So you can take it as the definition of Moonshine for my talk. But I just give you some facts and you can decide what you think about it. So the first question is then we have 39 cases and 23 of them has positive integers. What about other 16 of the 39? They have less, our conclusion is that they have less nice moonshine. Okay, let me explain these all undefined words. Less nice because they're negative, they have negative integers, so you have to introduce a grading on your Z2 grading on your representation. So the coefficients of these guys will be given by the difference of the characters, okay? And moonshine means they're connected. They have certain finite groups attached to them. And as far as we can see, these are rather small groups. They're there nevertheless, and we're looking for what replaces the Niemann lattices. And now about wave 2 world. Okay, for instance, again, wave 2 world, this gives you 34 in the case where you exclude M. And this list gives you a list of 19 in the wave 2. If you include M, include the frequent involution. So for instance, the first few is 6 plus 6. So what this notation just means that this is M, and the K, the subgroup of exact divisor is 1 and 6, okay? And so on. And the claim is that these guys, the corresponding distinguished Jacobi forms at wave 2, have also moonshine attached to them. And it's a version of Umbro moonshine. It's a dual version of Umbro moonshine, for instance. For instance, for this guy, the group is M24, which is the group when you, in Umbro moonshine, when you take the simplest, just A1 root systems. And this case corresponds to, you know, the next simplest case, and so on. So there's 5 cases that we have worked out explicitly, but this is, we think, more general. And, well, it might get better or worse. So if you write this unique Jacobi form satisfy our condition at wave 2, again, as a decomposition into so actually there is no sum here. So the nice thing about it is that there's only one independent component here. So let's just call it, okay. And then you define for all prime p a number that's p plus 1 divided by GCD of this. Now what you see is that for the M24 elements of order p, so if p is a divisor of the M24, then this number is always either 1 or 2, okay? But what if not, okay? You define it in general. Then you can, so conjecture, we have checked, but no proof yet. So conjecture is that for all prime, you can find, let's say, psi prime p, 6 plus 6, and which is a Jacobi form, and but now living at this group, congruent subgroup, such that 1, the starting power, if we also decompose it like this, okay, is minus SP times the leading powers. Okay, and 2, they all have integer coefficient, which is actually implied by 3, that if you rescale this canonical guy without P, so this canonical guy just add for SO2Z, we call it like this, such that, so if this canonical guy, if you want to do the M24 Moonshine, it starts with -2. So if you rescale it such that it also starts with SP, then all the coefficients are the same mod P, so it has this mod P congruence. Okay, so what is the consequence? The consequence is that there exists an infinite dimensional module for ZP, the cyclic group for all P, such that this is its greatest dimension and this is its character. So you might say that this is kind of Moonshine for all cyclic group, simple, which is, of course, very heretic, because we are used to think of Moonshine as something that's very exceptional, with very tight structure, and very unique everywhere. And so indeed, why can we do that? I just need, I'll finish in 1 more minute. How am I doing? Oh, okay, so I just finished. So we have shown the uniqueness in this direction, namely by going up in the index, but we can also go up in the level instead of, you know, the order of the element of the group if you want. Okay, and this is extremely ununique, although we have shown the uniqueness here. So you have cusp forms contributing and so on. So that's really a very different game from how we used to think of Moonshine. So, but because of the cusp forms, we know that cusp forms are important for connection to arithmetic geometry. So you can also connect this kind of mod P business to some statements about elliptic curves, but clearly I don't have time. I just am by saying, like, the lessons we learned is that there's a lot of structure in the Mach forms. They are really nice. And then, but in terms of Moonshine, in terms of how modular forms are connected to finite groups, we know very little, and it could possibly be conceivable that the connection is far more general than we think, and we certainly need a theory to understand the connection. Thank you.